Welcome to NPTEL MOOCs course on Computer Vision and Image Processing, Fundamentals and Applications. I have been discussing the concept of artificial neural network. Today I am going to discuss the concept of deep learning techniques. It would not be possible to discuss all the deep learning techniques in this computer vision course. So that is why I will briefly introduce the concept of deep learning, mainly the convolution neural networks and also autoencoders. How the deep learning is different from traditional pattern recognition system, that I am going to explain. So let us see the difference between the traditional pattern classification system and the deep learning techniques. So you can see here in this block diagram, I have shown one traditional pattern recognition system. You can see the input is the image, one image I am considering, and for classification or maybe for recognition of objects, I have to extract features from the image. So in this case I am considering the features, maybe shift feature or maybe the hog features I can consider, and after this I can apply some unsupervised or supervised classification techniques for object recognition. So that means the object is car that is available in the image that I can recognize. This is the traditional pattern recognition system, and already I have discussed about the image features. So we can consider shift features, or maybe we can consider hog features, or maybe we can consider texture features, or maybe the features like SERP, the local binary pattern, the color shift, color histograms. So all these features we can consider for image classification, object recognition. So in this case also I have shown one traditional pattern recognition system. So you can see the first one is the input is the image. After this we can extract the features. These are the handcrafted features. So maybe the features, the low level features, the edges we can consider, the boundaries we can consider, the shift we can consider, hog features we can consider. So these features we can consider for image recognition, image classification, object recognition, and after this we can apply the pattern recognition algorithms like support vector machine or maybe some other supervised or unsupervised techniques for object detection, object classification. So this is a typical traditional pattern recognition system. And now this is the structure of the deep learning. In this case you can see the deep learning is nothing but the cascade of nonlinear transformations. So you can see here it is a cascade of nonlinear transformations, and it is nothing but end-to-end learning. And in this case we consider hierarchical model that we consider. In this case, why it is called a deep? Because we want to extract more and more information from the input data. So suppose in this case I am considering one image. So I want to extract more and more information from the image. Maybe some low level information we can consider, or maybe the mid level information or the high level information, that is the features we can consider for image recognition, for image classification. So that is why it is called a deep learning approach, because I want to consider more and more information from the input image, and it is the end-to-end learning. And if you can see the performance of the deep learning algorithms and the traditional machine learning algorithms, here you can see that we are considering the size of the training data, and also we are considering the performance. If we have large amount of training data, then you can see the performance of the deep learning algorithms are much better as compared to traditional machine learning algorithms. But if I consider a small amount of training samples are available, suppose, then the traditional machine learning algorithms will be sufficient for a particular pattern classification problem or maybe the pattern recognition problem. So you can see the performance versus sample size. Sample size means number of training samples available for a particular classification problem. So now I am considering one supervised learning technique, that is the traditional pattern recognition model I am considering. So input image I am considering. After this, we have to extract handcrafted features, and after this we are considering the classifiers, maybe something like the support vector machine, random forest. So these type of classifiers we can consider. And output is object recognition. So outdoor scene, that means yes. If it is not the outdoor scene, it is no. So that is the image classification. So this is a block diagram for traditional pattern recognition system. Now I am considering the deep learning method. In this deep learning method, already I have mentioned, this is nothing but the cascade of nonlinear transformations. In this figure you can see I am considering one image, and from this image I can extract some low level features, or we can extract the mid level features, and after this we can extract the high level features. So maximum information I want to extract from the input image, that is why it is called the deep learning. Then more and more information I want to extract from the input data, and after this we can consider the classifier for object recognition, for object classification, or maybe the image recognition or image classification. So you can see the distinction between the traditional pattern recognition system and the deep learning system. So in the deep learning techniques, so already I have mentioned, so we have to extract low level features, mid level features, high level features. So in case of the image, if I consider maybe the pixels value or maybe the edges, I can consider as the low level features. For the mid level features, we can consider the texture or maybe the motif, and for the high level features we can consider the part of an object. So this type of features we can consider as high level features, that is the part of the object or maybe the object as a whole, that we can consider for image recognition, image classification. In case of the text recognition, what we can consider the low level information, the low level features, maybe the characters, the word we can consider. For the mid level features we can consider word group or maybe the clause we can consider, and if I consider the high level features, we can consider sentence or maybe the story we can consider as high level features. And one important point is, if I consider this approach, that is the deep learning approach, that is the hierarchical approach, that is very similar to the human cortex. That means what we are doing, the deep learning transforms its input representation into a high level one, and that is very similar to human cortex. Let us see the basic concept of the deep learning. So how it works. So first I will explain the simple artificial neural network and what are the main disadvantages of the artificial neural network, and why we need deep learning systems, why we need deep learning techniques. So in case of the artificial neural network, already I have explained that we have the inputs, that is the input layers, and we have the output is Y I am showing here, and also the hidden layers are available, and you can see the nodes corresponding to the hidden layers A1, A2, A3, A4. These are the nodes corresponding to the hidden layer, and if you see in the output we have the layer, the only one node is available. So I am considering this artificial neural network. So you can see the inputs x1, x2, x3, x4, these are the inputs, and corresponding to the hidden layer my nodes are A1, A2, A3, A4, and from the A1 to I will be getting the output. So this is a simple artificial neural network, and the training procedure already I have explained in case of the artificial neural network, that is the supervised learning. So first the sample level data we are considering, so that is why it is the supervised learning. After this, considering this sample level data, we are forwarding it through the network and get predictions. That is the meaning is I want to calculate the output of the artificial neural network, and already we know the desired output. So the difference between the desired output and the actual output, that is the error. So error should be back propagated to the input so that we can update the weights of the artificial neural networks. So that back propagation technique already I have explained in artificial neural network. So this is the concept of the training of artificial neural network. So we have to consider sample level data. After this, we have to determine the output of the artificial neural network, and we can determine the error. The error is nothing but the desired output minus actual output, and we have to minimize this error so that the error is back propagated to the input, and for this we have to update the weights of the artificial neural network. That means we are reducing the error in the output, and based on this we are adjusting the weights of the artificial neural network, and that is the training procedure, that is the supervised training procedure of the artificial neural network. So now I am considering a simple neural network. Here you can see. So I am considering 4 inputs, x1, x2, x3, x4, and one node I am considering A1, that is corresponding to the hidden layer. A1 I am considering, you can see. So my input is x1, x2, x3, x4, and the weights are W1, W2, W3, W4. So what will be the response in A1, that is the neuron is A1. So in this case you can determine the response. So response will be, you can see W1 is multiplied with x1, W2 is multiplied with x2, W3 is multiplied with x3, W4 is multiplied with x4, and after this I am considering the activation function. In my artificial neural network class, I explained the activation function, that is the sigmoid function we have considered. Now I am considering another activation function, that is called ReLU, rectified linear unit I am considering, and you can see this function, the maximum between 0 and x it is considered. So this concept of ReLU I will be discussing in this class. So we can find the response of this. So if I consider this max function instead of the sigmoid function, I can determine the output in the neuron, that is the response in the neuron A11 I can determine, that I can determine. Corresponding to the input is x1, x2, x3, x4, and I am considering the connected weights are W1, W2, W3, W4. Similarly, for all other hidden nodes A2, A3, A4, I can determine the response, and finally I can determine the response in the output neuron, that is A12 I can also determine, and finally I can consider one function, that is the softmax function I can consider, and that is the function is something like this, the softmax function. So it is an activation function, so that scales numbers into probabilities. So I will be getting the probabilities value. The probabilities lies between 0 and 1, and it is used for multi-class classification. So the softmax function is an activation function that scales numbers into probabilities. So I will be getting the probabilities for each and every classes. If I consider multiple classes, suppose for class 1 the probability is 0.2, for class 2 probability is 0.3, like this I will be getting the probabilities. Now in case of the artificial neural network, if you see the number of parameters, so you can see here the input I am considering x1, x2, x3, x4, and that means 4 input nodes I am considering, and 4 hidden nodes I am considering. The 4 hidden nodes are A11, A21, A31, A41. That is the second layer I am considering, and you can see corresponding to this I have the 4 cross 4 connections, 4 into 4 connections. After this, if I consider the second layer is A12. So corresponding to the second layer I have 4 connections. You can see the connections 1, 2, 3, 4, 4 connections, and finally I have the output. For output I have 1 connection. So that means you can see how many connections I have in this simple artificial neural network. And suppose if I consider one input image, the dimension is 400 into 400 into 3, that is 3 means I am considering the RGB image. So corresponding to this you can see, so number of parameters. So you can see the number of parameters. So this 400 into 400 into 3, that is nothing but 4,80,000 input nodes. So how many nodes are available? So x1, x2, x3 up to x 4,80,000 the number of nodes I am considering, input nodes. After this I am considering the hidden layer. Suppose the hidden layer also has 4,80,000 nodes. And if I consider this network, so number of parameters, so if you see the connections, the input connection and the first hidden layer connection, so 4,80,000 into 4,80,000 will be this. And after this if I consider the second connection, so how many connections between the second layer and the third layer? So it is again 4,80,000 plus one terminal, that is the connection between the second hidden layer and the output. So one terminal. So approximately it is 230 billion parameters you can see. And if I consider suppose 1000 nodes corresponding to the first hidden layer, so corresponding to this you can see we have 480 million parameters approximately. You can see the number of parameters in the artificial neural network. So it is too high. So that is why it is very difficult to train an artificial neural network, because we have to consider so many connections and so many weights we have to consider. So that is why it is very difficult to consider, or it is very difficult to train a particular artificial neural network for image classification, for image recognition. The number of parameters are too high. Again I am considering another example here. You can see I am considering input layer, hidden layer and the output layer. In the input layer we have 3 nodes that I am not considering now, and you can see in the hidden layer we have 4 nodes, and in the output layer we have 2 nodes, that means 2 neurons. So corresponding to hidden layer, if I consider sigma is the activation function, so what will be the output in the hidden layer? It is nothing but sigma W1 into x plus B1. So B1 I am considering, it is the bias terminal I am considering. And similarly if I consider the response in the output nodes, then in this case again I am considering the activation function sigma, that is the sigmoid function I am considering. So W2 into H, W2 is the weights, plus B2, B2 is the bias I am considering. Now in this case how do we train this artificial neural network? So if I do not consider input nodes, then how many neurons will be there? So in the hidden layer we have 4 neurons, and in the output we have 2 neurons, so total 6 neurons. And if you see the interconnections, that is the weights mainly, the interconnections means the weights. So how many weights? 3 into 4 corresponding to the connections between input and the hidden layer, and after this 4 into 2, that is the connection between the hidden layer and the output layer. So total 20 weights we have to consider. And if I consider the bias, so suppose for the hidden layer we have 4 bias terminals, so then in this case we will be getting 6 biases we are considering. So that means we have 26 learnable parameters in this neural network. That is too high. So how to resolve this problem? By considering the deep architecture, the deep networks. So for this I will discuss the concept of the convolution neural network. So what is the convolution neural network, and how the number of learnable parameters can be reduced. So for this I am considering one convolution layer. You can see I am considering the input image, and I am considering one filter, that is the convolution filter I am considering, and here it is I am considering the Laplacian filter. So what I can consider, corresponding to this input image, I can determine the convolution between the filter and the image. So I have the input image, I can determine the convolution between the input image and the filter. So for this I have to move the filter over the image, and I have to determine the convolution outputs. So for each and every pixels I have to do the convolution. So I have to place the marks, I have to place the filter over the image, and I have to determine the convolution. So for all the pixels of the image I have to determine the convolution. So you can see, suppose this is the image, the pixels value I am considering, and I have to place the marks over the image. I have to place the filter over the image, and after this I have to determine the convolution, and for all the pixels I have to do the convolutions. So I am showing it again. So like this you can see I am doing the convolutions, and after this I am getting the convolved image. Since I am considering the high pass filter, that is the Laplacian filter I am considering, so I will be getting the edges and the boundaries in the convolved image. So this is my convolved image. So in the convolved image I will be getting the edges and the boundaries. So let us see what is convolution. So suppose it is my input image I am considering. So it is a 4 by 4 image, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. These are the pixels I am considering. The pixel values are A, B, C, D like this, and I am considering the filter. The filter weights are W1, W2, W3, W4. So I am considering here W1, W2, W3, W4 like this. So it is W3 and W4. So this filter I am considering. After this I am determining the convolution. So how to determine the convolution, you can see. So I have to place the marks over the image and I have to determine the convolution. So just I am determining the convolution here, you can see. So corresponding to that filter, I am just multiplying the pixel value with the marks value. The marks means the filter value. So weight is W1, that is A into W1 plus B into W2 plus E into W3 plus F into W4 I am considering, and also I am considering the activation function. That activation function is F. So corresponding to this I will be getting the output. The output is H1 corresponding to the convolved image. And similarly, if I move the marks to the next pixel, then corresponding to this also I can determine the response of the marks. So you can see I can determine H2 just like the previous one. So I can determine H2 and I will be getting the value H2 here. So like this I have to do the convolution and I will be getting the feature map because I am extracting the feature from the image. So if I consider this is the filter, this filter can extract some important features from the image. So that is why I am getting the feature map corresponding to that particular filter. And in this case you can see the number of parameters for one feature map, it will be 4 because I am only considering the filter weights W1, W2, W3, W4. So that is why the number of parameters for one feature map will be only 4. But just you can see, you can do the comparison between the simple artificial neural network and this case. So by using the convolution operation, I can reduce the number of parameters. You can see the principle behind the convolution layers. So that means the number of parameters, the number of learnable parameters we can reduce. So for number of parameters for 100 feature maps will be only 4 into 100. So that is very less as compared to the earlier cases in case of the artificial neural networks. After this again I want to reduce the size of the feature map by the concept of the pooling. So these two pooling techniques I can apply. There are many techniques, but mainly one is the max pooling, another one is the average pooling we can consider. So suppose this is my input matrix, and what is the max pooling? The maximum output within a rectangular neighborhood. So suppose if I consider 2 by 2 neighborhood, that means 2 number of rows and 2 number of columns, that is 2 by 2 neighborhood I am considering. So maximum output within a rectangular neighborhood we have to determine. In case of the average pooling, what we have to do? Average output of a rectangular neighborhood we have to determine. Now I am only considering the max pooling. So corresponding to this, if you see here that corresponding to this input matrix, the output matrix will be 4, 5, 3, 4, because corresponding to the first neighborhood, that is a 2 by 2 neighborhood, the maximum value is 4. So that is why I am considering 4 here. And corresponding to the second neighborhood, so if you see the maximum value is 5. So 5 I am considering here. Corresponding to the third 2 by 2 neighborhood, I am considering the maximum value is 3. So 3 I am considering here, and corresponding to the last 2 by 2 neighborhood, so the maximum value is 4. So that is why I am considering 4. So that is the output matrix after max pooling. So that means I am reducing the size of the Fisher map. So Fisher map is obtained by the process of the convolution, and after this we can consider a pooling, the max pooling we can consider, so that the size of the Fisher map can be reduced. So here I am showing the structure of convolution neural network, one structure. So here you see I am only considering the filters and the max pool, this I am considering. So here you can see corresponding to this input image, I am considering number of filters in the convolution layer. So first this represents the filter and this represents the max pool. So first I am considering 64 filters for the convolution layer. After this again another convolution layer. After this I am considering one max pool layer. After this I am again considering 128 filter convolution layer. After this again another convolution layer. After this again the max pooling layer, you can see. So like this I can consider the cascade of the convolution layer and the max pool layer we can consider. And finally I am getting the max pool layer, I am getting this one, and that is converted into 1D vector. And after this I am considering one fully connected network for classification. So after the fully connected networks I will be getting the output mainly the classification of the objects present in an image. So you can see I am considering the cascade of these layers. One is the convolution layer, another one is a max pool layer. I am considering the cascade of this because already I have explained the deep learning means the cascade of nonlinear transformations, and it is nothing but end-to-end learning. So for learning we can use the backpropagation technique. So we can adjust the parameters of these layers by the process of the backpropagation learning, and you can see here. So final max pool layer, that is converted into 1D vector, and after this we can consider the fully connected layers. And you can see, so what will be the output of the fully connected layers? I will be getting the classes. So different classes I will be getting, that is the object recognition I am considering, living room, bedroom, kitchen, bathroom, outdoor, that is the image classification I am considering. Based on the input is the image I am considering. This is the concept of the convolution neural network. And in this illustration I am showing again the concept of the convolution. So I am considering the input matrix and I am considering the convolution 3 by 3 filter. And after this you can see the process of the convolution. So after convolution I will be getting the Fisher map. So you can see I am getting the Fisher map here. The next again I am showing the concept of the convolution. So I am considering the filter. Suppose this is my filter. So one filter I am considering. So I have to place the filter over the image, and after this I have to determine the convolution. I have to determine the response of the filter. So corresponding to the center pixel I am putting, or I am placing the filter over the image, and I have to determine the output, that is the convolution output I have to determine. And like this I have to shift the filter like this. For all the pixels of the image I have to do this. You can see just I am doing the convolution. So this is the concept of the convolution, how to determine the convolutions by using the filter. And I am getting the Fisher map. So you can see I am getting the Fisher map here. So this is my Fisher map after the convolution. And you can see here, if I consider this filter, and if I do the convolution with the help of this filter, then I will be getting the vertical edges I will be getting, because this is nothing but the high pass filter if I consider, because you can see the response here, response is 0 0 0. So that means I will be getting the vertical lines by considering this filter, that is the convolution filter. And like this I am giving some examples of the convolution filters to extract important features from the input image. So from the input image I can extract important information, important features of the images, the low level features, the mid level features and the high level features we can extract by considering the convolution filters. And here again I am showing the concept of the convolution layer. So we can consider multiple filters. Instead of considering only one filter, we can consider multiple filters. So in this case I am considering 200 into 200 image, and maybe we can consider 100 filters, and the filter size will be 10 into 10. Then corresponding to this I may have 10k parameters. So we have to do the convolutions. After getting the feature map, we have to apply the max pooling technique. The max pooling technique already I have explained. So you can see corresponding to the 2 by 2 neighborhood, the first neighborhood the maximum value is 6, corresponding to the second neighborhood the maximum value is 8, and like this I am considering the max pooling operations. So what is the importance of the pooling layer? So in this example you can see, let us assume the filter is an eye detector. So I want to detect the eye of this face that is present in the image. So how can we make the detection robust to the exact location of the eye? So first I have to do the convolution so that we can extract some features. After this I am applying the max pooling. You can see the pooling I am applying so that we can locate the location of the eye, because max pooling means I am taking the maximum value I am considering. So that means the exact spatial locations of the feature we can determine by considering the pooling operation. So finally I want to say that one, so you can see here, so if I consider one stage of this architecture, so I have the convolution layer and after this I have the pooling layer. So you can see corresponding to suppose this image I am applying number of filters. You can see the number of filters like this. So that is the filter bank. After this I am doing the convolution. So I will be getting the feature map. So you can see, so these are the feature maps. After this we can consider the activation function. The activation function is ReLU I can consider, and after this we can apply the pooling operation. We can apply the max pooling operation or maybe the average pooling operations, and after applying the pooling operations I will be getting the outputs. So output will be this. So this is one stage considering convolution layer and the pooling layer. And if I consider a typical architecture of the CNN, the convolution neural networks, so you can see we may have number of stages. So maybe the first stage, maybe the convolution pooling, again convolution pooling, convolution pooling. So we may have number of stages, and finally we have the fully connected layers, and output will be the class labels corresponding to the input image. So this is a typical architecture of the convolution neural network. Now let us consider learning of an image. So suppose in this example I am considering the back detector. That means I want to determine this portion of an image, this portion of the bird, and in this case the sum patterns are much smaller than the whole image and can represent a small region with fewer parameters. So how to represent that portion? By considering few parameters. So here you can see if I consider this portion is appearing here in the second image, in the different positions. So how to represent this? So if I consider suppose this one, that is the upper left back detector, and if I consider this one, that is the middle back detector. Now these two can be combined because these two can be compressed to the same parameters, because this pattern is appearing in another position of the image. So that is why if I consider the upper left back detector and the middle back detector, they can be compressed to the same parameters because they appear in different places of the image. So that means we can consider a filter for back detector. So a filter I am considering to detect the back, that is the back detector, and that is nothing but the convolution layer. So we have to do the convolution and I will be getting the feature map. So suppose I am considering the 6 by 6 image, the image is like this, and I am considering suppose filter 1, filter 2, filter 3 like this, and each filter can detect a small pattern. The pattern is suppose 3 by 3 size. So the filter size is 3 by 3 size, and the image size is 6 by 6, and we have to consider a network. So we have to learn the parameters of the network. So for this we are considering the filters, the filter 1, filter 2, and number of filters I am considering, and each filter can detect a small pattern. The pattern may be the 3 by 3 pattern. So let us see about this convolution procedure. So you can see, if I apply the convolution between the filter 1 and the image, so I will be getting the output something like this 3 minus 1, and I am considering the stride 1. That means the filter marks it is moved over the image by only 1 pixel. So that is why I am considering the stride 1. So if I consider the first position of the filter here, and if I consider the second position of the filter here, that means in the second position the filter is moved by 1 pixel. By only 1 pixel it is moved. So that is why it is called the stride 1. And if I consider the stride 2, that means the filter marks is moved by 2 pixels. So if I consider higher value of the stride, then in this case I can reduce the size of the feature map, and corresponding to this you can see I am getting the corresponding to the stride 1, I am getting the feature map something like this. And you can see corresponding to this filter, the filter 1, that can determine diagonal lines. That means what is the feature which can extract by the filter 1? The filter 1 can extract the diagonal lines. So that is why you can see the response is 3 corresponding to the diagonal lines. Here also you can see the response 3 corresponding to the diagonal lines present in an image. So by using the filter 1, I can extract the information of the diagonal line present in an image. So that filter I can consider, filter 1. And you can see after convolution I will be getting the feature map. The feature map will be something like this. And after this we can consider filter 2, and we have to repeat this for each and every filters. We have to do this procedure. So corresponding to filter 2 also I will be getting the feature map. That means I will be getting 2 cross 4 cross 4 matrix, that is the feature map. So feature maps obtained by considering filter 1 and filter 2. And in this example I am considering stride 1. So you can consider stride 2 also, like this you can consider. And if I consider a color image, suppose in color image we have 3 channels, R channel, G channel and the blue channel. Corresponding to these 3 channels we can determine the feature maps by considering filter 1, filter 2, filter 3, like this we can consider, and we can do the convolution between the image and the filters. So for this we have to consider R channel, G channel and the blue channel separately. So we have to do the convolution between the R channel and the filter, convolution between the G channel and the filter, convolution between the blue channel and the filter. We can do the convolution like this, and we will be getting the feature map. And in this case you can see the difference between the convolution and the fully connected, because in case of the fully connected network that is available in the artificial neural network, the number of parameters are too high. So that is why by the process of the convolution we can reduce the number of parameters. So by using the convolution operation you can see I can reduce the number of parameters. So here you can see I am applying the convolution between the image and the filters. So I am considering these filters and I am getting the feature map like this. But if I consider suppose this image, that is 6 by 6 image, if I consider fully connected neural network, so that means the input nodes we have 36 nodes, and after this we have the hidden layer, and after this we have the interconnections between the input layer and the hidden layer. So that is the fully connected neural network. So we need many parameters in case of the artificial neural network, but because of the convolution operation we can reduce the number of parameters. So here you can see I am applying the convolution, and by using the convolution I will be getting few parameters only as compared to fully connected networks. So in this case you can see I will be getting 3 here, that 3. What is the 3? The 3 is nothing but the result of the convolution between the image and the filter 1. So that portion of the image I am considering, and that is a convolution between that portion of the image and the filter 1. So output is 3. So that means corresponding to suppose this pixel, center pixel, I will be getting the value is suppose 3. So to get 3, so we are doing the connections like this. So only connect to 9 inputs, and it is not fully connected. So that means I am reducing the number of connections, number of parameters. In the second case you can see if I do the sharing of the weights, then in this case I can reduce the number of parameters. So corresponding to the second output, the second output is -1, second output is -1, I can share the weights of the layer, you can see, and by this process I can reduce the number of parameters. So sharing of the weights is possible. So by sharing the weights we can reduce the number of parameters. That is not possible in case of the fully connected neural networks. So that means the convolution helps in reducing number of parameters of the network. So the entire CNN, that is the whole CNN, will be like this. So my input is the image. After this I am doing the convolution. After this I am applying the max pooling, and again I am doing the convolution, and after this again I am applying the max pooling, and that can be repeated many times. The convolution max pooling, that can be repeated many times. After this the output of the max pooling, that is converted into 1D vector, that is flatten. The output of the max pooling, that can be converted into 1D vector, that is the flatten. After this we can consider a fully connected feed forward network, and after this I will be getting the outputs. So output means the number of classes I will be getting, that is the object detection we can do, whether it is a cat or a dog, that we can determine by considering this CNN, the convolution neural network. And what is the pooling operation actually? Why it is important? Because by using the pooling operation I can reduce the size of the feature map. So that means I can reduce the number of parameters. And one important point is subsampling pixels will not change the object. So that means you can see in this image I am considering this is the bird, and after this I am doing the subsampling, but the object will remain same. So that means subsampling will not change the object. We can subsample the pixels to make image smaller. So that means if I apply this max pooling operation, so what will be the advantage? The advantage will be fewer parameters to characterize the image. So we will have only few parameters to represent a particular image. So that means a CNN compress a fully connected network in two ways. The first one is reducing number of connections, that is one important point, and shared weights on the edges. So we can share the weights, and also we can apply the max pooling operations. So like this we can consider. So in this figure I am showing the same concept again. So convolution I am considering, and the activation function I am considering, the ReLU function I am considering, and after this you can see pooling operation I have shown. Again I have shown the convolution operation and the ReLU. Again I am considering the pooling operations, and finally the flattening of the feature maps we have done, and after this we have the fully connected neural network, that is the feed forward network. And corresponding to this you can see the outputs: the dog 0.94, cat 0.03, bird 0.02, that is the probabilities, and both 0.01. So these probabilities I am considering. These probabilities I am obtaining by considering the function. The function is the softmax, that already I have explained. So this is an activation function that scales numbers into probabilities. So softmax function I am considering. So I am getting the probabilities. The probability of dog is 0.94. the probability of cat is 0.03, like this I am considering. So this is one application of CNN for image classification. And I want to again highlight the concept of the activation function. The sigmoid function already I have explained in my class of artificial neural network. So you can see this is the sigmoid function. Fx is equal to 1 divided by 1 plus e to the power minus x, takes a real value number and squashes it into range between 0 and 1. So you can see the range is 0 and 1. And one problem of the sigmoid function is that sigmoid neurons saturate and kill gradients. That is the main problem of the sigmoid function, the saturation problem and the kills gradient, because we have to train the network based on the stochastic gradient descent algorithm, and that already I have explained, that is the gradient descent algorithm. So if I consider suppose the stochastic gradient descent algorithm, so you can see I am not explaining this concept, the stochastic gradient descent algorithm. So if I apply the sigmoid function, so it will saturate and kills the gradient during the training. And if the initial weights are too large, then the most of the neurons will be saturated. So that is the main problem of the sigmoid activation function. Another activation function is 10H. So that is the takes a real value number and squashes it into range between -1 and 1. So output range is -1 and 1. So that is the 10H function. But again the problem is the saturation. But one advantage is this output is zero centered, and you can see the 10H can be represented in terms of the scale sigmoid function. So 10H can be represented by the sigmoid function. But the problem is again the saturation problem. So that is why in most of the deep networks, in convolution neural networks, we used the ReLU function. That is, the ReLU function is Fx is equal to 0 for x less than 0, and it is equal to x for x greater than equal to 0. So it takes a real value number and thresholds it at a 0, Fx is equal to maximum of 0 and x. So you can see it is a linear function. So in case of the ReLU, that is a rectified linear unit, you can see the trains much faster, the training is faster and accelerates the convergence of the stochastic gradient descent. So that means the convergence will be fast, and due to linear nature, the saturation problem will be over. Due to the linear characteristics, the saturation problem will be eliminated. That means that prevents the gradient vanishing problem because of the linear characteristics, because it is linear function. So that concept I have not explained. So if you are interested about this stochastic gradient descent algorithm, so you can see the concept of the stochastic gradient descent algorithm, SGT, that you can see, and also the concept of the saturation, that is the gradient vanishing problem you can see. So based on this principle, most of the deep networks used the ReLU function. So this is about the convolution neural networks. Now I will discuss the concept of autoencoders. So what is autoencoders? Autoencoders are artificial neural networks. An autoencoder neural network is an unsupervised machine learning algorithm that applies backpropagation, setting the target values to be equal to the inputs. Also, autoencoders are used to reduce the size of the inputs into a smaller representations. And suppose if anyone needs the original data, they can reconstruct it from the compressed data. Here you can see the autoencoders are artificial neural networks and capable of learning efficient representation of the input data, and that is called codings, without any supervision. So that is why it is called unsupervised machine learning algorithm. The training set is unlabeled, and this coding typically have a much smaller dimensionality than the input data, making autoencoders useful for dimensionality reduction. So it is used to reduce the dimension of the input data. So in my next slide you can see the structure of the autoencoder. So I am showing one input image. After this I am showing the latent space representation of the input image, that is nothing but efficient representation of the input image, and that is compressed. So the dimension is reduced, you can see here. So from the input image I am considering the latent space representation. So dimension of the input image is reduced, and that is nothing but efficient representation of the input image. And after this, from that compressed image or maybe the latent space representation, I want to reconstruct the original image. So this is the reconstructed image. In the second figure I am considering one input image, maybe the noisy image, and after this I am considering one autoencoder. So this autoencoder compresses the input image. So for this I am considering the encoder. So I am getting the latent space representation. After this, from this representation, that is from the compressed data, I can reconstruct the output image. So what is the function of the encoder? That is used for efficient representation of the input data. So that means in a autoencoder I have input layer, I have a bottleneck layer, that is nothing but the hidden layer, and after this I have the output layer. So mainly I am considering three layers. One is the input layer, the first one is the input layer, after this the bottleneck layer, and after this I am considering the output layer. So it has encoder and the decoder. Now in this case, since I am doing the dimensionality reduction, then what is the difference between autoencoder and the PCA? So why autoencoders are preferred over PCA, the principal component analysis? So one point I can mention here, an autoencoder can learn nonlinear transformation with a nonlinear activation function and multiple layers. And that is one important point. Also, it is more efficient to learn several layers with an autoencoder rather than learn one huge transformation with PCA, because if I consider the PCA I have to consider a huge transformation, but in case of the autoencoder I can consider number of layers for efficient representation of data. Also I can make use of the pre-trained layers from another model to apply transfer learning to enhance the encoder and the decoder. That is also another advantage of the autoencoder over PCA. So what is encoder? Encoder means the part of the network compress the input into a latent space representation. So in the figure you can see I have shown one encoder. So this part of the network compress the input into a latent space representation. The encoder layer encodes the input image as a compressed representation in a reduced dimension. The compressed image is the distorted version of the original image. So I am doing the compression by considering the encoder. After this I am getting the code. So this part of the network represents the compressed input which is fed into the decoder. So I am getting the bottleneck layer, that is nothing but the latent space representation, and after this I have the decoder. So this layer decodes the encoded image back to the original dimension. The decoded image is a lossy reconstruction of the original image, and it is reconstructed from the latent space representation. So I can mention one property of the autoencoder. The autoencoders are only be able to compress the data similar to what they have been trained on. The decompressed output will be degraded compared to the original input. That is also one important point. That is, the decompressed output will be degraded compared to the original input. So this is about the autoencoder. Next, why we use autoencoders? So used for dimensionality reduction. So we can reduce the dimensionality of the input image. So that is why we are considering the autoencoder. And with the help of autoencoders, I can extract important features from the input image. So that is also one important point. That is, with the autoencoders, I can extract important features of the image. And they can be used for unsupervised pre-training of deep neural networks. So that is also another advantage. And one important point is they are capable of randomly generating new data that looks very similar to the training data, and that is called generative model. So I can give one example of the generative model in my next slide. So here you can see, for example, we could train an autoencoder on pictures of faces, and it would be able to generate new faces. So that is the generative model. So here you can see I am considering the autoencoder, and we can train the autoencoder on pictures of faces, and suppose I am considering these images. So this autoencoder will be able to generate new faces that I have shown in this figure. So that is one application of autoencoder. Now surprisingly, autoencoders work by simply learning to copy their inputs to their output. Then what is the importance of autoencoder? The importance is that autoencoder looks at the input and converts them to an efficient internal representation. That is, efficient internal representation of data, input data, and then spits out something that looks very closer to the inputs. That means it can reconstruct the inputs which looks very close to the original inputs. What is the meaning of the efficient internal representation? So I can give one example. The first sequence is 40, suppose 27, 25, 36, 81, 57, 10, 73, 19, 68. So this is my first sequence. First sequence I am considering. And let us consider another sequence, the second sequence. So second sequence is suppose 50, 25, 76, 38, 19, 58, 29, 88, 44, 22, 11, 34, 17, 52, 26, 13, 40 and 20 suppose. So I am considering two sequences. The first sequence is 40, 27 like this, and second sequence is 50, 25, 76. So like this I am considering. The question is, which one is the easiest to memorize? So first sequence is the short sequence, the second sequence is the long sequence. At the first glance, it would seem that the first sequence should be easier since it is much shorter as compared to the second sequence. But actually it is not. So if I consider the second sequence, two simple rules I can formulate. The first rule is, number one rule is, even numbers are followed by their half. So this is my first rule. Second rule is, odd numbers are followed by their triple plus 1. So I have these two rules to represent the second sequence. This second sequence is a very famous sequence. The name of the sequence is the Hailstone sequence. It is called the Hailstone sequence. So if I follow these two rules, it is easy to memorize the second sequence, as we have to remember first number and the length of the sequence. So by using these two rules, I can generate the second sequence. But in the first sequence, there are no rules. So that means in the second sequence, the one important point is existence of a pattern in the second sequence. That is nothing but that efficient internal representation. That is one example why autoencoders can be used for efficient internal representation of data. So here you can see, you can limit the size of the internal representations, or you can add noise to the inputs and train the network to recover the original inputs. So we can limit the size of the internal representation. That means we can compress the input data more, or we can add noise to the inputs and train the network to recover the original inputs. That means the autoencoder can be used for removing noise. That means the noise is eliminated and we can reconstruct the original input image. These constraints prevent the autoencoder from copying the input directly to the outputs, which forces it to learn efficient ways of representing data. So that concept already I have mentioned, that is efficient data representation by autoencoder. In short, the codings are by products of the autoencoders. So in this figure I have shown, in the first figure I am considering one noisy image, and after this I am considering the autoencoder. Autoencoder, you can see the encoder I am considering. After this I am considering the bottleneck layer, that is nothing but the hidden layer. After this I am considering the decoder, and I am considering the denoise image. So denoise image is reconstructed. The input is the noisy input image. The input seen by the autoencoder is not the raw image, the raw input, but stochastically the corrupted version. So that means a denoising autoencoder is trained to reconstruct the original input from the noisy version. That is the concept of the denoising autoencoder. So input is the noisy input, and after this I am considering the efficient representation of the input image. The autoencoder can learn this, and after this we can reconstruct the image by removing the noises. In the second case also I am showing the structure of the autoencoder. So you can see I have the input layer, hidden layer, and the output layer. So composition of autoencoder. So first is I need encoder or the recognition network that converts the input to an internal representation. So the first component is an encoder. After this, the next component is a decoder, or it is called generative network, that converts the internal representation to the outputs. So that means I have one encoder and another one is a decoder in autoencoder. So one is for compressing the input data, and after this a decoder or a generative network which can convert internal representation to the outputs. So here you can see I am showing one example of efficient data representation. I am considering one input image, that is nothing but the chessboard I am showing. After this the autoencoder can create the internal representation of the input image. After this it can reconstruct the input image. So output image, it is approximately equal to inputs. So for this I can give one example. Suppose I want to remember the position of the pieces in the chessboard. So these are my pieces. So expert chess players can easily memorize the position of all the pieces in a game by looking at the board just for 5 to 6 seconds. But it is very difficult for most of the people. So that is a task that most people would find impossible. So one important point is that pieces are placed in the realistic positions from one actual game, and they are not placed randomly. So what is the method basically they are doing, these expert chess players? They can learn the patterns of the input image or input data. So by looking at the chessboard, they can see the patterns, and based on these patterns, they can actually represent input data most efficiently, and after this they can also reconstruct the original patterns. Pattern means I am considering the position of the pieces in the chess board. So that is the concept of the efficient data representation. So you can see I have the inputs. After this I am considering internal representation. After this I can reconstruct back the original inputs. And the composition of autoencoders. So autoencoders typically has the same architecture as a multi-layer perception, except that the number of neurons in the output layer must be equal to the number of inputs. So in this figure you can see I have 3 inputs, x1, x2, x3. Similarly, I have 3 outputs, x1 dash, x2 dash and x3 dash. So that means number of neurons in the output layer must be equal to the number of inputs in a simple autoencoder. And you can see there is just one hidden layer composed of 2 neurons, that is the encoder, and one output layer composed of 3 neurons, that is the decoder. So that is I am showing the encoder, another one is the decoder. The outputs are called the reconstructions, since the autoencoders tries to reconstruct the inputs, and the cost function contains a reconstruction loss that penalize the model when the reconstructions are different from the inputs. So because the decoder I am considering that is used for the reconstruction of the input data, so for this what I am considering a loss function. If the output reconstructed data is not similar or not same as that of the inputs, then in this case the loss function will be more, the loss will be more, and based on this loss I can train the autoencoder. And here you can see the internal representation has a lower dimensionality than the input. So that is why if I consider the bottleneck layer, that is the internal representation, it is 2D instead of 3D, because I am considering the dimensionality reduction in the bottleneck layer. That is why autoencoder is said to be under complete, because I am reducing the dimensionality of the input data. So that is the concept of the encoder. So it is forced to learn the most important features in the input data and drop the unimportant ones. So that is nothing but efficient representation of the input data. And there are many variants of autoencoder. I am not going to discuss all these autoencoders. One is the sparse autoencoder, another one is the stack autoencoder, one is the variational autoencoder, one is the denoising autoencoder, and one is the contractive autoencoder. So if you are interested, then you can read some research papers regarding these autoencoders, different types of autoencoders. So I am not going to discuss about these autoencoders, but the main concept of the autoencoder I have already explained. So in this class I discussed the concept of the convolution neural networks. What are the disadvantages of the artificial neural networks? So how to reduce number of parameters by considering convolution layer, that concept I have discussed. After this I discussed the concept of the pooling layer, and after this I discussed the concept of the fully connected layer. Also I discussed about activation functions. One is the sigmoid function, another one is the 10H function, and another one is the ReLU activation function. After this briefly I discussed the concept of the autoencoder. I am not discussing in detail because it is not possible to discuss all the deep learning techniques in this computer vision course. So I hope you can understand the basic concept of the deep learning and also the convolution neural networks and the autoencoder. Let me stop here today. Thank you.